Hello friends, today we will discuss about the recognition of the fault in the field. We will discuss some features. With the help of these features, we can determine and recognize the faults in the field. So let's start. This is a very beautiful picture from the southern India. Here we can see this is a host type of structure, and this is bounded by from one side a normal fault from this direction, and this one also. This block is moving towards down one direction, and this one also. So it's look like a host structure. So we have three criteria. Based on these three criteria, we can identify the faults in the field. First one is feature intrinsic to the faults, means those features those are associated with the faults. With the help of associated features, we can recognize the faults in the field. Then second criteria is the effect of the fault on the geological or stratigraphical units. So based on the effect of stratigraphical units, we can identify the faults in the field as well. Then third one is physiographic features, means topographical features. Those represent the faulting or existence of any fault or discontinuity in the region. So first one, features those are associated with the faults. So basically, first criteria is associated rock. So we have two types of rock. Those we can get means nearby in the fault region. First one is cataclastic rock, and second one is mylonitic rocks. So cataclastic rock basically form in those areas where fault exists or less than 10 to 15 meters. So if we have a fault that is means extend up to 10 to 15 kilometer, we will get cataclastic rock. In cataclastic rock, generally these cataclastic rocks are there is no preferred orientation, and they form as a sharp angular fragments. So based on this cataclastic rock, we can divide into three categories based on the size of the fragments. First one is mega breccia, then breccia and micro breccia. So mega breccia, if the grain size is more than 0.5 meter, so that type of, or you can say more than 0.5 mm, that is known as mega breccia, and the percentage of the matrix is less than 30%. In breccia, 1 to 500 mm and less than 30% matrix. Micro breccia, if the size of the grain less than 1 mm, that is known as micro breccia. There is one more classification based on the class concentration, and it is given by Mott and Hodwork in 2008. So first one is crackle breccia. Crackle breccia, actually in crackle breccia, what we have class concentration varies from 100% to 75%. As we can see in this sketch, the class concentration is 100%, 80%, 75%. So that is known as crackle breccia, when the percentage of the these grains less and varies from 70% to you can say this one is 58, approximately 55%. That is known as mosaic breccia, means more or less, or we can say roughly, if we have a rock that has mixed type of character, we can say mosaic breccia. Then chaotic breccia, if the grain less means vary from less than, or we can say means constant up to 55%, that is known as chaotic breccia. So we can see another criteria is based on the myotic rock. So myotic rock basically is a stretch or highly strain rock, shows the lineation parallel to the major shear zone. As we can see here, we have a lineation. These are the lineations. But this myotic rock basically form where the fault form below 10 to 15 kilometer. So basically such type of rock associated with the ductile shear zone. Okay, so first one is based on this criteria, we can classify this myotic rock into three categories. First one is this one is the ultramyelonite, then mylonite and protomyelonite. So this one is first figure number A is protomyelonite, where the grain size is more, means more more than 90%. So this one is the protomyelonite, and it's decreasing towards the ultramyelonite. This one is mylonite. intermediate condition, and when the grain size means grains are less and the glassy material is very high, that's known as ultramilonite. And ultramilonite also form means at higher temperature, you can say more than 600 degrees centigrade temperature ultramilonite is formed. And the myelinite is varies from 350 to 600 degrees centigrade temperature. And this protomyelinite is associated at the crystal deformation, or we can say this is the product or result of the means rocks of the those form below 300 degrees centigrade temperature. So myelitic rocks are foliated and lineated. Interlocking grains boundaries sutured to polygonal means the grain boundary angles is more 120 degrees centigrade. So they classified as we have discussed protomyelinite, myelinite and ultramyelinite. So here the grain size is 50 micrometer in protomyelinite, 50 to 10 myelinite. Ultramyelinite is less than 10 micrometer. So in ultramyelinite the matrix is more than 90%. And as we have discussed already, the size and the percentage of the matrix is decreased towards the protomyelinite, or we can say the size of the or the percentage of the grain is decreased towards the ultramyelinite. So this is the schematic diagram of the fault. Here we can associate it intrinsic features. In the fault, this sigma 1 is vertical, and here we can see this is a fault zone, or we can say this is a damage zone. So here this below 300, or we can say 0 to 300 degrees centigrade temperature, we will get brittle type of a structure. In brittle type of a structure, we have what we have protomyelinite. Then move towards the 300 to 450 degrees centigrade, we have brittle ductile transition. In brittle ductile transition, we start pseudotecholites, cataclasites, some cataclasite also we occurred here. And below 300 degrees centigrade, we have cataclasites. Below 300, the percentage of the cataclasite is decreasing suddenly, as we can see from this sign to this sign, and the discrete myelonite start forming here, and the pseudotecholite is also start forming here. Then below 450 degrees centigrade, ductile structures form, and the discrete myelonite diminish and start this ultramyelonite zone here. And pseudotecholites is associated or confined up to 450 degrees centigrade. Okay, so this is the schematic. And then pseudotecholites are the breccia, or we can say microbreccia, contain matrix of crystal less than 1 micrometer and a small amount of glass or devitrified. When the devitrification or glass percentage is increasing, as we can see here, this dark material is the glassy material. So if the grain is embedded in the glassy materials, so such type of rock or product is known as pseudotecholites. This one is cohesive, glassy or very fine grain. They form during, and in this, if we can see here, this embedded grain should be associated with the country rock. Means the grain of embedded grain should be from the country rock. And their general result brittle ductile deformation, as we have discussed earlier. And one important point, pseudotecholites are lower in sodium and calcium percentage, but higher in potassium and silica percentage. So basically pseudotecholites form there where the silica rich rocks are associated or occurred. Okay, then the microscope, in microscope, pseudotecholites shows the isotropic phenomena. If you rotate the stage of the microscope, you will get same appearance of the color throughout the stage or rotation. So these are isotropic in the nature. Then effect of folding on geologic or stratigraphic units. So basically the effect of the folding on the geologic or stratigraphic unit means we get some discontinuity. Suppose that we are getting the Cambrian strata in a region and suddenly we are getting this Jurassic strata. So there is some breakage in the means age or stratigraphic units. So such type of feature occurs due to faulting and may be occurs due to unconformity. For example, this is the very panoramic view of the Doon Valley, Dehradun Valley, and this is a thrust here. This one is the MBT, and we can see here this light color strata. This one is this fault scarp, and this fault scarp here we have some alternate slices here. So this one is the foot wall, this one is the hanging wall. Here one slice is here, this is the sudden inclination here, then we have inclination here, then here, then here. So we have slices of imbrications. So slices of imbrications are the volume of the rock, those are bounded by the fault from the both sides. So this is the evidence, clear evidences of the faulting in the region. And one more thing, here the elevation is suddenly increasing here. So this one is the hanging wall and suddenly decreasing towards valley side. So this one is formed due to faulting, and we have slicing, normal fault slicing over here. Okay, so this is the geomorphological evidences in the valley. Next one, repetition and omission of strata. This criteria is basically usable for the subsurface exploration. If suppose that we drill uh, any area and we are getting repetition strata, as in this sketch, this is dolomite, then we have mafic type of material, then again we are getting dolomite in the core sample. So we are getting repetition constantly. So it may be due to faulting. One more thing, and here in this sketch, the dolomite is omitting here. So here suddenly we change the lithology. Here there is no repetition. So here we have to take the precaution, because this repetition of a strata or omission of a strata may be occurred due to transgression and regression process in sedimentary rock strata. So we have to be very take care to means convey there is fault is exist there or not. Then drag faults and rollover faults. Drag faults and rollover faults, very common structure, those are associated with the discontinuities or fault. As we can see here, this is a fault plane. If this is hanging wall, this hanging wall is moving towards upward direction, this is moving upward direction, and this is the stagnant force. So that's why we have dragging here. So this is dragging, and this dragging is opposite towards each other. So this block is moving towards upward direction, this block is moving towards downward direction. So this one is the drag fault due to form due to the movement of the relay block, two blocks against or along one plane of the fault planes. Here in the rollover folds, this one is the rollover anticline fold or antiform fold. This is a normal fold. Due to gravity, this whole blocks move towards the downward direction. So that's why we get a rollover type of a structure. Here we can ask, or we get confusion between the drag type of folding and rollover folding. This drag type of folding in extension is very small, but rollover folds are very big in expansion. Okay, and drag type, in the case of the drag type of folding, we get two opposite sense of curvature. This one is means we have curvature toward this direction and we have curvature toward this direction. But in rollover, we have no such type of feature, means we don't have opposite type of curvature here. So we, based on this criteria, we can differentiate between rollover type of fold and drag type of folding. Then physiographic criteria. Physiographic criteria is very important. If suddenly we are getting some means suppose that we have a fault plane here and shear zone here. So this, due to this faulting, we have some linear valley. So linear valley may be formed due to some linear feature. So that linear feature may be a fault, may be a joint, or may be some intrusions. So we have to check out. But this linear valley may indicate some disturbance, geological disturbance. So based on one criteria, we can get conclusion there is a fault or not. We have to look over there for more evidences also. But this linear valley also gives some means indications there is something linear feature, whether that is fault or joint or any other features. Then scars. Due to faulting, some state transition between two blocks or state or cliff type structures form due to faulting. Those are known as scarp. If these scarps are associated with the fault, known as fault scarps. So these fault scarps are very important physiographic features. Those very useful to identify the fault. Then springs. Due to faulting, may get some springs, because faulting intersect any aquifer, and due to that intersecting, we can get some springs over the surface. Then sag ponding, stagnant water. The sag ponding, as we can see here, this is a valley, this is one another valley, this displaced toward this direction, this one is displaced toward this direction. So we have some extension here. So this formed due to some pull apart type of basin. So this pull apart type of basin formed due to faulting. Linear ridges, linear ridges also formed due to, may also form due to faulting. Then offsetting in the drainage, as we can see here, offsetting of the drainage may be due to faulting. Setter ridges. Setter ridges means suddenly due to faulting, we are getting obstacles in the course of the river or in the course of the drainage, that's known as setter ridges. Okay, and some other features also associated with the faults, like if suppose that we have some paleo channels, abandoned paleo channels, those may be associated with the faults due to form, due to, means river can change their course due to faulting. So based on these criteria, we can recognize very easily these faults in the field. I hope you will enjoy this video. Thank you very much.